First I'd like to thank the organizers. It's really my great honor to join this NCTS Annual Meeting and share some of my work with you. So today I will talk about waveguide method predictions from cosmological simulations. I'm Hsi Yu Schive from NTU. So this outline of my talk, I will introduce this waveguide method, or actually it's now often called the fuzzy guard method. You heard talk from that. This fuzzy miracle. So this talk I will use waveguide method and fuzzy guard method interchangeably. So introduce the model characteristic and cosmological simulations, and then comparisons with observations and some ongoing projects, and finally some major challenges of this model. Okay, so first, what's the characteristic of this FDM or waveguide method model? So in this talk, usually I will call this Psi DM because here we are solving actually the Schrödinger equation, so we are solving the wave function side, so we call it Psi DM. So the waveguide model is composed of extremely light particles with the particle mass on the order of 10 to the minus 22 electron volt. So you already heard from Matt's talk that this fuzzy miracle, if you still remember it, the mass is normalized to this 10 to the minus 22 electron volt. So my talk will focus on using different observations to explain why this value is preferred. So it's about 10 to the 31 times lighter than the conventional standard CDM model. And because of such a small particle mass, its de Broglie wavelength becomes astronomical scale on the kiloparsec scale. So it will show many wave-like properties such as interference. That's why we call it waveguide method. So for the model reviews, you can refer to these two papers. So the governing equation is very simple actually, just this Schrödinger single particle, Schrödinger Poisson equation in the co-moving coordinate, because we are doing cosmology simulations. So this is the Schrödinger equation, you all know that, and the psi here is the wave function. And the phi here is the potential, which can be evaluated by solving this Poisson equation in the co-moving coordinate, where this A is the scale factor, this Y is the cosmic background measure. So one of the most important properties of this model is that it only has a single free parameter, which is the particle mass m psi here. So one of the most important tasks in my talk or in this study is to try to constrain this particle mass from different observations. So to study about method, also there are many particle experts here. So you can study from the particle physics, so compare theory with observations. But I'm more like astrophysics, so I compare the prediction from simulations with observations. So that would be the approach adopted in this one. So another important feature of this waveguide model is that there is an effective quantum pressure that will suppress the small-scale structures. So this feature can be mostly seen by rewriting this Schrödinger Poisson equation into these conservation laws, which are very similar to the Euler equation for hydrodynamics. So just the continuity equation, the momentum equation. So in comparison, this is the momentum equation for hydrogen. As you can see, the only difference between these two equations is the first term on the right-hand side. So this is the pressure term. So the only difference is the form of this pressure. So by comparing these two terms, we can actually derive the expression for this quantum pressure, which is actually the stress tensor. Okay, so this quantum pressure plays a very important role that can help distinguish this FDM model with other like CDM model or waveguide method. Because it has pressure, you can define the corresponding gene steps, which is the characteristic scale where gravity balances pressure, right? So above this scale, gravity dominates. So IDM will behave like CDM because they are both dominated by gravity. But below this scale, quantum pressure dominates, which will suppress the small-scale structures. And it's well known that the standard CDM model tends to overpredict the small-scale structures. So this quantum pressure can help to solve this issue. And you also heard in the previous talk about this core problem in the cell interaction. So that will also be another important prediction in this model. This quantum pressure will also help suppress this divergent density profile in the innermost region, so to produce a core. But the core profile actually looks different from the prediction of other central dark matter models, like bone market or SID. Here, the core profile looks different. So next I'll talk about cosmological simulations. So the numerical challenges of conducting this kind of wave parameter simulations lies in the fact that here we are simulating the evolution of wave function, which can behave very differently from the ordinary method. So here example, so this is a slice, the image of density slice in our cosmological simulation. So you have several massive halos here, and the black region here is just like background density. So it has no exciting features at all, it's just void. But it is density, which is wave function squared. So not wave function, we are simulating wave function. So what does the wave function look like? So wave function actually looks like this. So this is what we are actually simulating. Note that these two figures represent exactly the same slice. We just take square, so the square of wave function is density, right? So we are solving wave function, but we eventually want to get the density to compare with observations. So you see there are many wave patterns like ripples in this figure. So the physical origin of these ripples is actually very simple. They are all just plane waves because in quantum mechanics you know that on certain principle tells you that the wavelength is inversely proportional to the momentum. So when the dark matter here approaches these massive halos because of gravity, so their velocity gets higher and higher, of course, and the corresponding wavelengths become shorter and shorter. So in the region far from, say, the halos, the velocity is lower, so the wavelength is longer, and in the region close to the halo, the wavelength becomes shorter and shorter. So what does this figure tell us? It tells us that when conducting this kind of wave dark matter simulations, it's very numerical challenge because even in this very boring region, we still need adequate spatial and temporal resolution to resolve these waves because we are actually solving wave function. In a conventional CDM model, you can probably apply very low resolution here because you don't really care. But here we do care, so we have to resolve all these term waves. Otherwise, if you do not have sufficient resolution, say their propagation speed becomes wrong, so your accretion rate becomes wrong, so your halo mass function becomes wrong. So, and you can imagine that the larger the system, so the more massive the halo, say if this is not a small halo, this is a cluster, then the inflow velocity gets much higher. So the wavelength becomes much shorter. So this is actually a very small simulation. This simulation box is only like 1 or 2 megaparsecs on each side. It's very, very numerical expensive. So in short, ultra high resolution is required, and that's one of the reasons we have developed this gamma code, which stands for Jupiter Accelerated Adaptive Refinement code, which is about 1 to 2 orders of magnitude faster than other conventional AMR code. But in this talk I won't talk about this. So this figure compares the large-scale structures predicted by the CDM model and the CDM model. So the large-scale structures. You see that the large-scale structures predicted by these two models are almost indistinguishable. So the position of both halos and these filaments, they are all very similar. So this result is actually expected and desirable because on scales much larger than the gene scale I just mentioned, the evolution should be dominated by gravity in both cases. So you should not be able to distinguish these two models. And also desirable because it's well known that the CDM model is very consistent with observations on large scales, say on the cluster scale. So we definitely don't want to provide any surprising results on these scales. So this is just to make sure that, okay, on the large scale, the model is okay. But what about the small scale? So that's more interesting. So this figure shows a close-up of the density distribution of cosmological FEM simulation. So we find interference patterns everywhere. So from the filaments connecting different halos. So this is a halo, this is a small halo. So the filaments connecting different halos to these isotropic density granulations throughout each halo. And the most important and most interesting thing is that we find this core, this constant density core. So you heard it from the self-interaction talk by Professor Yu. that in this model we also find a prominent constant density core in the center of halo. And that's very different from the CDM prediction, which would predict this thermodynamic profile. So the density profile should diverge in the center. Here, it's not the case. So later I'll show you that actually this core profile is more consistent with observations in many cases. Okay, sorry. So the next question I want to ask is whether there is always a prominent constant density core in the center of every halo. So to answer this question, we conduct extensive merger simulations with different configurations. So this movie just show you one example. So at the beginning, we have like a kind of random distribution. Let's see, yeah. So we just let it collapse and relax to see what's the final system after the system relaxed. And the answer is yes. We always find this constant density core in the center of every halo in our simulations. Moreover, we found that these constant density core are actually solidomes. So solidomes are the isotropic, non-dispersive ground state solution in this Schrodinger Poisson equation. So we found that this core profile can fit very well with this theoretical solidome solution. So here, the black data points are numerical simulation results. The red line is the analytical solidome profile. So that can be fit very well with each other. So different line is different halo. So you see, this is the core, the constant density core I'm referring to. So this line is just for reference. This is the unaffected profile. So density goes to infinity in the center. But for the sliding model, density approach a constant value. Okay, so the next question I want to ask is whether there is a well-defined core-halo relation. In other words, for a given halo, can we predict the property of this core? It's solid core. So the answer is again yes. So this figure shows this core-halo relation. So the horizontal axis is halo mass. The vertical axis is core mass. Data points are our simulations, cosmological simulations. This dashed line is our theoretical prediction. So here we demonstrate from both numerical simulations and theoretical argument that this core mass should be proportional to the 1/3 power of halo mass with an additional this redshift-dependent factor. So based on this relation, we have provided or predicted many unique properties of the sliding model. For example, dwarf gases should have kilopascal scale cores. There should be a minimum halo mass on the order of 10 to the 8 solar mass. For a Milky Way-sized galaxy, there should be also a prominent core within about 100 parsec and with a mass on the order of 10 to the 9 solar mass. And these solidome cores should be more compact at higher ratio, so at early times. So I emphasize that these quantitative predictions have converted sliding model for the first time to become directly testable. So now we can actually compare this model with observations thanks to these quantitative predictions. So that's very important. So this model now becomes more popular because now you can do real experiments. So in the next several slides, I'll focus on comparisons with observations. But before showing quantitative results, I want to briefly summarize the main features of the sliding model. So as I mentioned, you will have solidome cores in the center of every halo. You will suppress low mass galaxies, and there are density granules, these density perturbations throughout the entire halo. So how do we probe these properties? How do we compare them with observations? How do we test them? So for example, to study the solidome cores, we can compare it with the dwarf spiral gases, the stellar distribution in these dwarf gases. To study the suppression of low mass galaxies, we can compare it with the galaxy mass function. So we can count how many galaxies is observed and whether that's consistent with the theoretical prediction. We can also compare with the observed ground-management history. To study the density granules, we can use this graphene dancing flux anomaly, which I will introduce quickly. So first, we use the stellar distribution in dwarf galaxies to compare whether the observed stellar distribution is consistent with the predicted solidum profile. Because in these dwarf galaxies, it's well known that they are dark matter dominated. So for given dark matter mass profile from the solidum profile, and a given observed stellar velocity dispersion profile, combine these two factors, we can derive the corresponding stellar light profile and compare with observations, and use that to constrain our free model parameters, which is the particle mass here. So this figure shows the stellar number density as a function of radius. Black data points with arrow bars are observations. So using this approach, we determine a best fit Psi particle mass, which is about 0.8, normalized to 10 to the minus 22 electron volt. So that's the first quantitative estimation of this number by comparing with observations. We can also determine a best fit core radius, so the size, the radius of the solidum core, which is about 1 kilopascal. So it's accurate because that's the wavelength corresponding to this system. So the red line here shows the best fit Psi profile, the profile predicted by Psi. This is stellar distribution profile. You see the red line is very consistent with the observational data. But the blue line is the best fit profile predicted by the standard CDM model. You can see that the fit is relatively not that well. And it's mainly because, as I mentioned, in the CDM profile, the density is diverged in the center. So the mass is too concentrated in the center and it becomes not consistent with observations. But of course, it's not that fair. I should be fair to say that this is just pure CDM prediction. So CDM can always include this baronic physics, then you have lots of degree of freedom to play with. So here is that, I should not say that CDM is wrong. I'm not saying that. I'm saying that for this sliding model, you don't have to rely on this complicated baronic physics that can already explain the observed core profile in many systems. So we have to extend this work to other dwarf galaxies. So this figure shows the velocity dispersion profile of 6 different classical dwarf galaxies in our Milky Way. Again, there are points with arrow bars are observations, and blue lines are the best fit Psi prediction. So again, we find the best fit particle mass, which is about 1.2. So again, consistent with the value I just showed you that derived only from using only the 4next data. So here I want to emphasize that we only have one free parameter here. We can only choose one particle mass. So we cannot choose different particle mass for different galaxies. So this is a joint analysis. Yeah. These 6 different blue lines, they all share the same particle mass. So you cannot use particle mass of 10 to minus 21 here, minus 23 here. That's not fair. So you have to apply a joint analysis. So it's actually quite surprised that you can find a very consistent particle mass for different systems. So that's further support. That's why we prefer this value. So next, I want to talk about the suppression of high-risk galaxies, especially the suppression of low-mass galaxies at high redshift. So now we have fixed the particle mass. So fix it by comparing with dwarf galaxies. This value is fixed to 10 to the minus 22 electron volt. So we can no longer play with it. The question we can ask is that for this given particle mass, does the Psi model suppress too many high-risk galaxies because of this quantum pressure? Or actually the CDM model produce too many high-risk galaxies? So the upper panels are the CDM simulations. You can see there are small clumps here. They are low-mass halos. For the corresponding Psi halos, Psi simulation, you see, you still get these massive halos, but all these small-scale structures are suppressed because of the quantum effect. So to answer this question, we can compare with the observed galaxy luminosity function. So the luminosity function gives you the galaxy number density as a function of luminosity. So here, the luminosity function as a function of the galaxy luminosity. So from the bright end to the faint end at 4 different redshifts, from redshift 4 to 10. Data points, these black data points are observations. This black dot line are the CDM prediction. The red, green, and the blue lines are the CDM predictions with different particle mass. So the red line has the largest particle mass, the blue line has the smallest particle mass. Now remember that the smaller the particle mass, the stronger the suppression. So here, these results show that, okay, CDM actually is very consistent with observations. But also the red and blue and the green lines, they are also consistent with observations. However, these blue lines lies below the observational data point, especially at lower redshift at band end. It means that for this given particle mass, actually is suppressed too many low mass galaxies. So you can imagine I can use this approach to obtain a lower limit of particle mass. So this result actually preferred the CDM model. But we can obtain a lower limit of this particle mass, which is again about 1.2. So it's always around this 10 to the minus 22 electron volt. So that's quite surprising. And also, it's much better, it's much more consistent with the Wong garment. So based on this result, we predict that the luminous function should turn over slowly. So it should turn over. It will not diverge. It should turn over slowly around UV magnitude of minus 16, above redshift 4. So this numerical range lies just beyond the purely detectable range here. But it will soon become direct testable with forthcoming observations like James Webb Space Telescope. And actually can also be tested with highly magnified galaxies using Hubble Space Telescope. So the prediction in the band end is very different. The CDM predict that there should be a strong suppression. The CDM predict that, okay, the lower the mass, then there should be abundance of low mass galaxies. So whether we can observe them or not, we'll definitely distinguish these two models. Okay, so for given luminous function, actually, we can also calculate the corresponding Thomson optical depth of the cosmic microwave background. Because as you heard from the talk of Professor Chen, that galaxies will emit high photons, which will realize the universe and produce free electrons to interact with CMB. So the more the galaxies, the larger the optical depth. So this figure shows the optical depth, Thomson optical depth, as a function of the limiting luminosity, which is the faintest galaxy that we assume that can contribute to reionization. Now, Planck observation in 2015 observed an optical depth about 0.07, which is indicated by this cross-hatched region. So this region is the observation. Now, this is the CDM prediction. Red and green and blue lines are the CDM prediction. So you can see how, okay, CDM predict the larger optical depth because it predicts many small galaxies. But this figure shows that the CDM model can also be consistent with observations. And the smaller the particle mass, the smaller the optical depth, which is expected. And from that, you can derive, again, a lower limit of particle mass, which is about 0.7. So this constraint is not very strong, but again, consistent with all the constraints I showed you previously. Another feature you find very interesting here is that the CDM prediction is very sensitive to the assumed limiting luminosity, because CDM predict many faint galaxies. So it really depends on where you want to cut. You want to assume that's your assumption that, okay, below this luminosity, it should not contribute to reionization. Otherwise, this curve just goes infinity. But the CDM prediction actually is very insensitive to the assumed limiting luminosity, because faint galaxies are suppressed anyway. So it doesn't matter what kind of cutting luminosity you assume. So it means that in this case, the CDM prediction is actually more, say, is less model dependent, so which is not a good property. Okay. It's also known that the gravitational lensing will introduce a bias to observe gas number density, which this effect is referred to as this magnification bias. Now there are two competing factors in this effect. First of all, the lens image will become brighter, so it will increase the observed gas number density. On the other hand, lensing will reduce the effective field of view, which will reduce observed gas number density. So these two competing factors, the magnified luminosity and the reduced field of view, have opposite effect on the gas count. So for given say, field angle, so how many gases you observe for a given muscle. Now, the fact that the small gases inside it are strongly suppressed has a dramatic impact on the prediction of magnification bias. And I illustrate this property in the lower two figures. So here, this black line, dashed line, is the field of view. The field stars are bright gases that can be observed. Unfilled stars are gases that cannot be observed because they are either too thin or they just lie outside the field. Now with lensing in the CDM model, the observed gas number density will increase because with lensing there will be many thin gases getting magnified to become detectable. In comparison for CDM model, after lensing, the observed gas number density will decrease because there are much fewer thin gases to be magnified. So in short, after lensing, the CDM gas number density will increase, but the CDM gas number density will decrease. So most importantly, this apparent difference is directly testable. So this is a paper we just made this year, discussed about how these predictions compare with observations. And it turns out that I also prefer the CDM model. Okay, so I'll quickly go through some ongoing project and the major challenges of this model. So we have been working on this to study these density granulations. So this density granulation is one of the most, say, unique predictions in this model that can distinguish CDM from not only the CDM model, but also all other alternative argument model because this very unique feature in this very particular argument model. So we have pinned down several unique properties of this density perturbations. First, they have comparable size with the central soliton, suggesting that they are also isothermal. So, like the talk of Professor Yu about the self-impression, he mentioned that in the central region it was thermalized. So it's very similar to that case. Furthermore, this density granulation has 100% modulation, meaning that the density can literally go to zero. So the perturbation is not actually perturbation, this fluctuation is very large. So it's very different from the CDM prediction. Also, this density granulation is everywhere. So it distributes throughout the entire halo. It's not like the substructures in the CDM model. In the CDM model, you have like a subhalo here, a satellite here. It's not the subhalo here. It's just density fluctuations everywhere. So that's very different from the CDM prediction. So I'll probably just skip these slides. So basically, we can use lensing flux anomalies to probe these density perturbations, these density granulations predicted by the CDM model. So for the CDM model, the prediction is very different. But this result is quite preliminary. So let's not talk about that in too much detail. So we are also studying the tidal stripping of CDM halos. So there are many interesting questions we can ask. For example, our CDM halo is more or less vulnerable to tidal disruption. So on one hand, they have prominent soliton core, which are ground state, so it should be more, difficult to destroy them. On the other hand, the common effect actually may make it more vulnerable to tidal disruption. We are also curious whether this tidal stripping might affect the core halo vision. I talked about that previously, and whether it can help expand the observed high mass to light ratios in those real galaxies. So here is a simulation with that small CDM halo orbit around a Milky Way sized galaxy. So at least it demonstrates that for Hubble time it survived. So otherwise, if it cannot survive, it means that okay, all these small galaxies should be destroyed. But we do observe these galaxies. So that means that this model can be problematic. But at least this preliminary results show that okay, these small CDM halos can survive. Okay, so we are also studying the heating of star clusters. So in many galaxies, we find that there's a small star cluster in the center. And because this soliton will also oscillate, so there are recent papers suggesting that this soliton oscillation may actually heat up the central star cluster. So basically just pumping energy. So star cluster will be heated up and diffuse away. So it cannot survive. So we should not observe this star cluster. So that's the challenge of this model. Our recent simulation suggests that, okay, this black line is the stellar number density. The blue line is the soliton. So soliton is oscillating, but star cluster survive for whole time, suggesting that this heating mechanism is not as efficient as one might expect. So that's also good. But it's also a preliminary result. So I will just say, very quickly go through the main challenge. So one thing is that whether this sighting model only suppresses the gases. So does it suppress too many gases? Because now we observe more and more small gases. So maybe we suppress much. And also about one hour forest, but let's skip it. Another thing is about as you heard from the previous talk about this rotation curve. So the self-interaction parameter can fit this curve very well. But sighting can do it or not. Actually, I'm not sure. I would say that it can be quite challenging because we have this soliton. This soliton corresponds to this upturn, to this rise of the rotation curve. So, and this feature is sometimes missing in many systems. So it means that in this system we do not find evidence to support the existence of these solitons. So maybe that's wrong. So that's a big challenge for this model. Okay, so thank you very much.
Okay, time for questions.
So if this step is an axion, then there's a coordinate coupling, which has a tiny numerical value, but the occupation number is so large that it can be important. And one thing it can do is it can cause some part of this stuff to collapse into small lumps, which, have you thought about what that would do? I mean, it might give you a sort of combination, I mean, because I think then it behaves more or less like a standard particle matter, but not all of them.
Helps collapse, like perhaps almost. Yeah, we haven't included that in our simulation, but we one thing we've been working on is we call it like the extreme axion model. Is that, as I mentioned, actually, in the standard particle model, it tends to suppress too many small-scale structures when considering like the non-mount forest or the gas number density, the satellite number density in the local system. So we have been working on this extreme axial model. Actually, we include this cosine potential, and we assume that axial angle is very close to say close to pi. So it's quite strange, but we assume that the x actually at the beginning reside on top of this potential. And that introduced another degree of freedom to play with the initial condition. So actually, for a given particle mass, that additional degree of freedom actually can produce more substructures. It will still have a strong suppression at Fn, but it will produce more substructures compared to the standard project particle model for the same particle mass. That's very important because for the same particle mass, so it's still consistent with all gases. But because different initial power spectrum, it may predict more substructures that's more consistent with, say, non-mount forest. So that's one thing we have been working on.
Okay.
Thanks for the interesting talk. I just had one question about the role of baryons, because you noted that you were comparing against CDM-only simulations, and that's not totally fair.
Yeah, it's not fair.
Then you also said that it was interesting that the wave dark matter didn't need baryons to do this and that, whereas CDM did. I don't understand the sort of psychology of that. I think the baryons are there, so it's not a question of heating them or not. It's the question of what do they do.
So probably it's important to find systems that say have very few baryons. Say even low surface runs gases. So where we may actually theoretically predict that baryon feedback should not be that strong. So that's the ideal case to compare different models. So for punctual gases, for manageable gases, the mass volume ratio is so large that we are not sure whether feedback can be that efficient. So I'm not saying that CDM failed, but it's good to have this model that we don't have to rely, say, very strong feedback, even though we already know the mass volume ratio is so large. Yeah, but still, yeah, I should clarify that I'm not saying baryonic physics is not important here. So this is very preliminary result in that sense.
So I guess my question is really like, what would it take to include baryons in these simulations?
Actually, it's quite, it depends on what kind of baryon physics. The code that we are developing has hydro because it's designed for hydrodynamics. So it's very straightforward to include both. But to include more like complicated feedback mechanism, of course, that requires other experts. Yeah, numerical is very straightforward because we all have both modules. Yeah, we can even include magnetic field. It's all there. We can also do transformation with both CDM model and SciDM model. Maybe happen.
Very interesting call. So these wave patterns, do you expect at some point that you can somehow detect such wave patterns in observations in some situation?
We're hoping that. So that's why we emphasize the importance of these density granulations. That's basically just the interference patterns. So. Sorry. Okay. So this density, this is a project density. So actually already smooths out these fluctuations, but you still see these local density clump. They are all just interference patterns. So that's why we are working on this density flux anomaly. So that can be used to probe whether the underlying dense gas, the density distribution of dense gas is smooth or not. So if it's smooth, sorry, I skipped this actually. So the flux anomaly in strong density means that if the dense gas has a very smooth density distribution, the sum of the magnification of these four images produced by density should be 0. But observation you will find 10 to 15 residues. So observation you find that the sum of their magnifications is not 0, suggesting that the dense gas actually has the density distribution is not that smooth. So for the SciDM model, we predict that this residue R is always very large. Suggests that you should always find this flux anomaly in every system because there are always density fluctuation. There's no way to skip that. For the CDM model, you have substructures. So sometimes you find this flux anomaly, sometimes you don't. But the prediction for SciDM is very different. You should always find this flux anomaly. That's just a prediction. So we are not saying that the observations prefer this model. But that's one thing can be used to distinguish it.
Okay, last one.
Just one quick question about that. What about Gaia data? Because in principle, you can reconstruct a lot about the dark matter density profile in the Milky Way.
In the Milky Way, right? In the Milky Way, the one thing that's very interesting is, again, this central solidum. So, there are several things we can use the Milky Way observation to probe this model. One thing is the central solidum. So the solidum in Milky Way has a size of about 100 parsecs. So we predict that inside that region you should have a significant fraction of mass from barometer. But that's also hard for observations to tell because it's also in that region the gas pressure is very high. So that's one thing. And also you can study the global cluster stellar streams. So these streams may also be sensitive to these density perturbations. So it's possible that if this perturbation is too strong, it may again heat up the stream. So the stream will look different, or maybe the stream will be destroyed. But we do find these streams. So that means that this model fails. But so far, I think theoretical arguments suggest that the heating is not that efficient. But again, if we have better and better data, I think we can use that data stream to constrain this model.
Okay, any further question? Okay, so let's thank all the speakers in our presentation.